In this video, we will look at how to generate a command file for a simple cantilevered beam analysis using Efficient software. This beam is a rectangular hollow section with a dimension of 100 millimeters by 50 millimeters by 5. It is fixed at one end and a load of 2000 Newton is applied on the other end. The mesh for this FE analysis is in MED format. In this mesh, the fix node is given a node group name of fix, and the node on which load is applied is given a node group name of load. Start Efficient if not started already. Click on the first tab Mesh Type if not on this tab. Select Start Debut for is this a new analysis or continuation. Select MED for the type of mesh and select Linear Static for the type of calculation. Click on the tab Analysis Type and then select Mechanical Beam for the type of analysis in the drop-down section. Click on tab Material and select Carbon Steel from the material database. Enter CS for material name. One thing to note here is that any name you give should be less than 8 characters in length. Leave the default values of Young's modulus, which is 210 gigapascals or 2.1E5 megapascals, Poisson's ratio of 0.3, and density of 7.8 E-9 ton per millimeter cube. Type in all for is assigned to and then click Add. By doing this, carbon steel material properties will be added and applied to all the components in the analysis. Select tab Element Type. Here, we'll add information about the beam element. Select Beam from Type of Element. Select Rectangle for section type. Enter Guide for is assigned to, as this is the name given to the mesh group in the mesh. Enter Phi for thickness in Y direction. Here Y is the width in local coordinates in code Aster. Keep thickness in Z blank as this RHS section has a uniform thickness. Z is the height in local coordinates in code Aster. Enter 100 for section width HY and 50 for section height HZ. Click Add and the section properties will be added to the command file. Now let's concentrate on the Boundary Conditions tab. For type of boundary condition, let's select Degrees of Freedom on Node Group. Enter Fixed for Boundary Conditions name. This is not the name of the node group, but a name reference that will hold information of the boundary condition. Enter Fix for is assigned to. This name has to be exactly same as that defined in the mesh file. As this is a boundary condition fixed in all directions, enter 0 for all dx, dy, dz, drx, dry, and drz. Click on Add and the boundary condition will be added to the command file. Next, let's add that 2000 Newton load. Click on the tab Loads. Enter Force Z in load name. This is again a reference name by which we will define load. Select Force on Node for load type. Enter Load for is assigned to. This name has to be exactly same as that defined in the mesh file. As we want to define load of 2000 newtons in Z direction, enter 2000 in FZ. Click on Add and the load will be added to the command file. Finally, click on the Output tab. Efficient is intelligent and selects all options available for beam analysis for the user to select. Select one or many as you want in your output file. If you don't add anything in this tab, Efficient by default will add deflection to the command file. As we want all output, I'll select Add All. Hooray! We made it! But before we celebrate, let's save the command file. Click on Save Command File, and in the window that pops up, select the location of file to be saved. I'll save the command file here. Just enter the name. Here I'll enter beam.comm. Don't forget to add .comm at the end. Click on Save. When the file will be saved, a confirmation message like this will pop up informing the user for the same. Click on OK. Congratulations! You generated your first command file. Now let's have a look at the command file. So I'll go to Explorer, and there is beam.comm file. I'll open it, and that's the file. I won't go in detail in the command file as it is out of scope of this course, but I encourage you to use this command file in finite element analysis of your own.